So the next speaker will be Nathaniel Alco. Nathaniel, are you ready?
Yep.
Yeah, okay. So then the talk is about abstract clones of abstract syntax. Please go ahead, Nathaniel.
Thank you very much for the introduction, and thank you to the organizers of the conference for arranging it and giving us the chance to speak about our work. I'd also quickly like to thank Marcello Fiori, who's my supervisor, for introducing me to many of the topics that come up in this work. So today I'm going to be talking about some joint work with Dylan McDermott on an approach to simple type theory using abstract clones. And I'm going to explain what the words in my title mean very soon, so don't worry if you're not familiar with them. So first of all, what does this mean? What does abstract syntax mean? Well, I think we can all agree that we want to be able to reason about programming languages, to be able to describe their behavior and their properties. However, this is frequently done by reasoning about their concrete syntax. But this can be a bit misleading because really the concrete syntax isn't a very good reflection of the abstract structure. So we'd rather be able to reason about their properties directly from their structure without worrying about what their syntax looks like. And so any formalism that captures the abstract structure of a programming language without recourse to its concrete grammar or syntax is called abstract syntax. What do I mean when I say programming languages here? Because this is quite a vague term. Well, for us in this talk and in our paper, by programming language, we really mean a simple type theory. And so this consists of a collection of types, a collection of terms in variable contexts, some notion of substitution. In our case, we're going to consider simultaneous substitution. One could also consider single variable substitution. It doesn't make a huge difference. This will just be more convenient for our case. We want some notion of operations on terms. So for instance, pairing of terms, projection from pairs, lambda abstraction, function application, this sort of thing. And note that we are including variable binding operations. So things like lambda abstraction in these operations. And then we want some equations on our terms, which will dictate their behavior. So this includes things like beta and eta laws for type theories. So note that if we just consider the subset of this structure, consisting of the terms, the simultaneous substitution, the operations, and the equational laws, we get what's known as an equational theory, which is a concept from universal algebra. So this dictates the structure of things like groups, rings, monoids, and so on. And if in addition we consider types, then we get a multisorted equational theory. And we additionally cover things like modules for rings, group actions, monoid actions, and so on. So by simple type theory, we really mean a multisorted equational theory with variable binding operators. And this formalism has been previously considered. It was introduced by Fiori and Her in 2010 under the name multisorted second order equational theory, where second order refers to the fact that we can bind variables. A first order operator is just an operator from universal algebra. So again, I've been a little bit vague in what I mean, a bit hand-wavy, in that I've said the sort of things we want to have in a simple type theory, but I haven't said precisely how to specify them. So the question is, what structure axiomatizes this list here? And in fact, there are many formalisms in the literature already that capture this structure. So originally, in 1999, Fiori, Plotkin, and Churi introduced sigma monoids to capture algebraic structure with variable binding operations. In their case, they were looking at the single sorted case, but it was later extended to the multi-sorted or type setting. And then there are other formalisms like second order algebraic theories, which are an extension of Levier theories from categorical algebra. And then various people have studied structured notions of concepts from category theory, like monads and relative monads, and Cartesian multicategories. And there are several papers in this vein too. But there's a potential problem with these approaches in that they make use of sophisticated category theoretic arguments. And this isn't a problem per se, because category theory is a very powerful and useful language. But it is a problem when, say, you want to assume that or you don't want to assume your readers are familiar with category theory, or you yourself are not comfortable using category theory. So though we can see that abstract syntax is very useful for studying programming languages, it can be inaccessible to people who are not familiar with the high level of category theory required to understand the techniques. So the question is there an approach to abstract syntax that does not require a high level of category theory, but is still powerful enough to prove the results that we care about? And this is the motivating question for our work. And it turns out the answer is yes, unsurprisingly, otherwise I wouldn't be giving the talk. But in actual fact, the approach that we're going to propose has already been used in the literature. So I think the first occurrence was in a thesis of Mahmoud in 2011, where she showed that the sigma monoids from the previous slide are equivalent to a certain class of abstract clones with algebraic structure. And also Hyland in 2017 used abstract clones with algebraic structure to capture the unitype lambda-calculus and prove various properties. However, these treatments appear within larger categorical works, and so you still require category theory to understand the treatment. And certainly the use of abstract clones in this fashion hasn't been proposed expressly for simple type theories, and so it's hard to have an introduction to these ideas without learning a lot of background first. So really the purpose of our paper is to provide an introduction to these techniques so people can start using abstract clones to prove theorems about programming languages using abstract syntax. So I've been using this word a little bit already, but I haven't defined it. So what do I mean by abstract clone? Well, abstract clones were originally introduced in the 1960s as a way to axiomatize universal algebraic structures in general. And by this, I mean that algebraic structures in general, such as groups, rings, monoids, and so on, all share similar properties. And so abstract clones axiomatize the similar properties that these structures have. So we have an abstract clone for each algebraic structure. So there's an abstract clone for groups, an abstract clone for rings, an abstract clone for monoids, and so on. So roughly, an abstract clone consists of a collection of terms in variable contexts and simultaneous substitution operations. And to see how this corresponds to algebraic structure, or if we have a term in n variables, we can equivalently consider this as an operation taking n inputs and giving a single output. So if we think of the usual set theoretic definition of a monoid, we have a set x and a binary operation x squared x, so a function from the product of x with itself to x, which takes a pair of terms and returns the multiplication of those two terms. And then we also have a unit, which is represented by an element of x, or equivalently a function from x to the 0, i.e. the one element set, to x. And then we also have some equations, but we're not going to worry too much about those now. So these two perspectives, operations or functions and terms, are the way we convert between the structure of a clone and algebraic structure. I'm going to be a bit more precise about that in just a moment, but that's the idea to have in mind. So I mentioned from the start that abstract clones are equivalent to many other concepts from category theory, all of which were either introduced to capture algebraic structure or were later proved to be equivalent to algebraic structure. So all of these concepts are equivalent to the classical concept of equational theory that I mentioned before. So just to name a few, we have algebraic theories or Levere theories from categorical algebra, Cartesian operads or Cartesian multicategories, then various kinds of monads and relative monads. And then we have the original approach to abstract syntax in this style using substitution algebras or monoids for a substitution tensor product on categories of presheaves. So these are all equivalent to abstract clones, but we propose that abstract clones are a much simpler structure, and so they're much more useful if you don't want to use complex category theory to go about proving things for abstract syntax. So let me give you a slightly more precise definition of an abstract clone. So we're going to fix a set of types from the start. And then we're going to say an abstract clone consists of a set of terms for each context and each type. So by context here, I really mean a list of types. The variable name's not important. And then for each variable in each context, we're going to have a term, i.e. an element of one of these sets that corresponds to the projection of the variable from the context. So in other words, our terms are going to be closed under variables. And then we're also going to have a function on our sets of terms representing simultaneous substitution. And I've written it here as a natural deduction rule, but really precisely it's represented by a function on the sets. And these functions have to satisfy laws that axiomatize simultaneous substitution. So for instance, substitution should be associative. Substituting a term for a variable should result in the term itself, and so on. So let me revisit this idea from before a little more precisely, how abstract clones can capture algebraic structure. Consider a binary operator, f, so it takes two operands. On the left-hand side and the right-hand side, I presented two different ways to present this operation using natural deduction type-theoretic rules. So on the left-hand side, we're representing the operator as a term in two variables. And so the operands are represented by the variables. And on the right-hand side, we've got an inference rule that has two premises. And the conclusion then depends on the two premises. So the operands are corresponding to the premises. And really, these are equivalent. They're just different styles of seeing the same operation. To go from the left to the right, we can substitute s and t for x and y. And to go from the right to the left, we can consider the two variable context. Gamma is equal to x, y, and then s equals x and t equals y. But we think about these slightly differently. So on the left-hand side, we're thinking of operators as being terms that are parameterized by their contexts. And on the right-hand side, we're thinking of operators as being families of inference rules that are indexed by the context. And note that the context on the right-hand side has to be homogeneous. So all the premises and the conclusion have the same context. Now, in a clone, these two ways of seeing an operator are represented two different ways. So on the left-hand side, we have f being an element of the set of terms in two variables. And on the right, we're representing it more traditionally as a function of sets. So taking two terms in the same context and returning a new term, indexed over all the context gamma. And these are equivalent. So having a structure on the left corresponds to a structure on the right and vice versa. It is only the left-hand side which is intrinsic to the abstract clone itself, because the abstract clone specifies these sets of terms, not algebraic structure on top of them. So the left-hand side is intrinsic to the clone, but sort of induces the right-hand side. Now, I said that abstract clones capture algebraic structure, but we've already said that we're interested in programming languages. So in particular, we want to also capture variable binding structure, which is not captured by algebraic structure. So if we take the unitype lambda-calculus as an example, we have two rules, the function application rule and the lambda abstraction rule. And then we have some equations as well, but we won't worry about those. And we can see that the unitype lambda-calculus, or the terms of the unitype lambda-calculus, form an abstract clone, because we can take the terms of the unitype lambda-calculus, and these are exactly the terms of the abstract clone, and a simultaneous substitution of the clone corresponds to the syntactic notion of substitution in the lambda-calculus. Now, because the function application operation is algebraic, because all of the contexts are the same, it means that it's captured intrinsically by the correct clone structure, in that we have an element app of the set of terms in two variables, and this in turn induces our operation at the top, i.e. taking two terms in the same context and turning in a new term. However, lambda abstraction is not an algebraic operation because the contexts are different. So there's something new going on here because we're binding a variable. So therefore, it's not captured intrinsically by the clone structure. However, if we pretend for a moment that somehow it was captured by the clone structure, by analogy to the previous slide, it should induce an operation as a function on the sets of terms. And in particular, it should induce this, this family of functions, which takes a term in an extended context and returns a term in the original context. And this is indexed over all context gamma. And the insight is that it suffices to axiomatize this algebraic structure on top of the clone in order to capture variable binding operations. So we're sort of axiomatizing the derived structure that we want rather than it being intrinsic to the clone itself. And from another perspective, another way to say this is that universal algebraic structure, as in the classical setting, is captured by looking at operations and functions on sets. So for instance, in a monoid, we have a binary operation, and this is represented by a function from the product of m with itself to m, along with some equations and also a unit. However, if we want to consider variable binding structure, we instead need to look at algebraic structure on abstract clones, so operations on the term sets of the abstract clone. And the important thing is that we don't require the context to be homogeneous in our abstract clones. They can be heterogeneous in order to capture variable binding structure. So by moving from algebraic structure on sets to algebraic structure on clones, we capture variable binding. So this is sort of the motivating idea. To capture simple type theories, we consider abstract clones equipped with algebraic structure in this sense. And this leads to a conceptually elegant approach to abstract syntax that is practical in the sense that we can prove things we want to prove using this and without recourse to categorical arguments. So what does this look like a bit more practically? Well, recall that a simple type theory is usually presented by natural deduction rules. So we have rules for formation, introduction, elimination, computation, and so on. Now, natural deduction rules are typically concrete syntax. So they're specified informally, and we're all happy, we all know what they mean, but traditionally they're not a formal notion. So the formal notion that corresponds to natural deduction rules, in this case, is called a second order presentation. And this is analogous to the presentations from universal algebra. So second order presentation consists of a signature of variable binding operators. So a signature means that we have a list of operators represented by their arities and co-arities, and the arity may be binding. So we can capture things like lambda abstraction. And then we also have a set of equations on the derived terms, which are formed by closing the operators under substitution. And then we're going to define an algebra for a presentation to be an abstract clone equipped with the algebraic structure that interprets the presentation. Or in other words, it interprets the natural deduction rules of the simple type theory. So the algebra should really be thought of as the abstract syntax for simple type theories that interpret our rules. However, we're usually interested in a particular algebra, i.e. the one that's generated freely from the rules. This is called the free algebra. And this is really what we mean when we talk about the abstract syntax of a programming language. So if we want the canonical one, we're interested in the free algebra. And in our paper, we show that every second order presentation emits a free algebra. And intuitively, this is given by the sort of obvious, well-known construction of closing the rules under derivations inductively. And to do this a bit more precisely, we use the second order equational logic of Fiore and Her, which is an extension of the equational logic of universal algebra and equational logic to have metavariables as well as variables. And the metavariables represent variable binding structure. Now, it's all very good and well if we have an abstract structure that captures a type theory, but it's not very useful unless we can prove things with it. So in our paper, we justify this point of view by proving several well-known theorems in this framework to give sort of new light on known results and to show that using abstract clones can lead to conceptually elegant arguments for results that we're interested in. So in particular, we show how abstract clones can be used to form logical relations arguments. In our paper, we give 3 such proofs. We prove the adequacy of the set-theoretic model of the simple type lambda-calculus. We prove normalization for simple type lambda-calculus, and we prove that with and without global state. So as a very high-level overview, the natural reduction rules of a programming language correspond to the concrete syntax, and we want to abstract away from that. So from the natural reduction rules, we can generate a second-order presentation, which is the formal counterpart to the natural reduction rules. We can then look at the algebras for the second-order presentation, which are these abstract clones equipped with suitable structure. And these algebras represent the abstract syntax. And so these abstract clones, the algebraic structure, are equivalent to the formalisms I listed near the beginning. So the more category theoretic techniques. So you can do anything with abstract clones, you can do with the other techniques, but the abstract clones have a much simpler definition. They're often much more convenient to work with. And then once you have these abstract clones, you can then prove theorems about the programming language you started with using more abstract and elegant techniques than one would usually use on concrete syntax, in particular because we can use general meta-theorems applied to simple type theories in general, as opposed to having to perform the same arguments over and over again for each type theory. So in our paper in particular, we give an induction principle for second-order syntax. And this is the core of our logical relations arguments. And this is a general technique that can be used for any simple type theory defined in this way. And it gives a general method to work with simple type theories. Okay, so I'm going to finish up here. So in conclusion, our proposal is that abstract clones provide a viable and practical approach to abstract syntax. And they're especially well suited when one wants to avoid category theoretic arguments. But even if you are fond of using category theory, abstract clones are still very useful because the definition is conceptually much simpler than many of the alternatives. And so we think that abstract clones are a useful technique in general for abstract syntax. For more details, I'm going to refer you to our paper where we talk about everything in more detail and give many more examples. So thank you all for listening. And yeah, I'm happy to take questions.
Yeah, thanks, Nathanael. So there's a question from the audience by Joe Wells. I just read it. It's in the chat window. It says, thanks for a great talk. Can you please agree to the permanent public availability? I don't know. Okay, so this is actually an organizational question. Yeah, so it asks if the recording will be available permanently, and if the slides will be available, the PDF of the slides will be available. I think that the second question addresses the speaker. Yeah.
Yeah, certainly I'll make the slides available on my website. And yeah, my understanding is that the talk itself will be recorded and uploaded somewhere.
Yep, thanks. And then there's a question from Paul. Please go ahead, Paul.
Hi, Nathaniel. Thanks for the talk. I wonder if, just to clarify, when you talk about these second order equations, are they in context? I mean, I wonder because in the case of something like the eta law for the sum type and the eta law for the zero type, especially the eta law for the zero type, it's really critical that it takes place in a context, because any two terms are equal if the context within a context that includes something of type zero. But if the context if the context is empty, then it's a very different story. So I wonder if your second order equations are in context or not.
Yeah, they are in context. So the presentations we use are at least equivalent to the ones that appear in the work of Fiore and Her. And so, yeah, they're in context.
So do you think you would be able to deal with eta law for zero type, for example?
It's not an example I thought of. I'd imagine so, but
okay, I'd be interested to know that, but maybe I can discuss afterwards. Thank you.
Thanks. And then there's another question from the audience. It's from Kenichi Asai. I just read it. Have you formalized the technique in some proof assistants such as Cocoa or Agda?
No, we haven't. But I am aware that there's ongoing work to formalize a very similar formalism by a student of Marcelo Fiore. So yeah, I think soon there will be a formalization of something very similar to this approach.
Thanks. And then there's a hand raised by Sam. Please go ahead, Sam.
Oh, yeah, thanks for a nice talk. I wanted to ask when I was looking at abstract clones corresponding to second order algebraic theories, I found myself looking at enriched abstract clones, and I'm wondering whether there's, and that has to do perhaps with Paul's question about the context, because I was enriching in presheaf category, and so the enrichment was there. So I'm wondering whether that's here or it's hidden somewhere. And that's important from the point of view of monads with effects, because you want strong monads or enriched monads there as well. So I'm just wondering whether that ties in at all with what you've been doing.
Thanks for the question. So if I understand correctly, so when we talk about abstract clones with algebraic structure,
yeah,
there's a slight sort of separation in that the algebraic structure provided the abstract clone is sort of free from presentation in the Levere theory style, whereas the binding algebraic structure is on top of the clone. And so this is not presentation free.
Right.
Whereas if you move to enriched clones, I believe everything is presentation free, even the second order structure.
Right.
So I think these two approaches are equivalent, but the enriched setting is possibly slightly more categorical. And I expect that one could unwind the definitions to get a definition free from category theory if one wanted to. So I imagine they're equivalent, but it would be useful to double check.
All right, thanks. Interesting.
Okay. We have like 1 or 2 minutes for further questions. Yeah, okay. Is it?
I'm still on mute. Can I ask another question then? If there's, you were talking about higher order logical frameworks, and it reminded me of like 20 years ago. So Gordon Plotkin was proposing something called dumbbell. I don't know if you came across that. And Robin Adams was proposing type framework, and they were sort of they called them lambda-free logical frameworks. I wonder if they tie into the sorts of things you're talking about here.
So I keep muting myself and then I'm not finding the unmute button. Yes, I'm familiar with Adam's work on the logical frameworks, not dumbbell though, I'll have to look into that. So my understanding is that Adam's framework would correspond to a setting in which we don't just have second order operations and second order equations, but we have an infinite hierarchy. I guess my answer is I imagine one could formalize this structure in the clone-like setting. And in fact, Dylan and I have thought about this a little bit in our work in higher order algebraic theories. But we haven't worked out the details. So I'd say this is still an open question.
Thanks, interesting. Thanks.
Thanks. So then let's thank the speaker, Nathaniel, again. Thank you. Thanks.